Okay, yeah, welcome everybody. It's good to see that so many of you are here. So welcome to Popl and to Languages for Inference. So this is the 7th year in the series, 3 years of the workshop on probabilistic programming semantics, and then it's been called Languages for Inference for the 4th year now. And thanks especially to the chairs of the program committee, Christine Tesson and Jean-Baptiste Tristan, and to all the program committee for putting together what looks to be a very exciting program for this year. And we're delighted to have as the first speaker, Sam Staton from Oxford, talking about abstract types in probabilistic programming.
Yeah, thanks Cameron, and yeah, thanks to the organizers for what looked like an interesting day. This talk is about abstract types in probabilistic programming, so it sort of spans Popl and LAFI and inference, and so there's sort of two themes. One is abstract types, which is a Popl topic, I guess, and the other is probabilistic programming. I don't know what the backgrounds of all of you are, so if you don't know probabilistic programming, I'll show you a bit later, but it's roughly a method for describing statistical models by writing programs. And if you don't know what abstract types are, let's have a chat about those. And I'll do it by contrasting first with concrete types. So concrete types, I think, are types where you can inspect the values on the nose immediately. If you see a value of a concrete type, you know what it is. So, for example, an integer, you know what that is. Boolean, you know it's either true or false. Pairs of Booleans. Real numbers, are they concrete or not? Well, that's a thing to debate. I think it's an interesting question. I think I often think that they're concrete. We can look at a real number and know what it is, but of course there's lots of interesting things about computability and so on there. What about abstract types then? Well, they're things where we need a bit more effort to understand what the values of them are. So for example, function types, functions from reals to reals perhaps, or second order functions. So the integration functional is something that takes a function from reals to reals and gives back a real, the expected value or the integral of the function. Those are function types. Also, I would say finite lists of concrete things are maybe concrete, but as soon as we start looking at infinite structures, they start to be more abstract. It's harder to inspect them. So an infinite stream of Booleans, I would say, is rather an abstract type. But really, when types, they're typically talking about existential types or modules. And over here, I put a little piece of Java. I'll show some Haskell modules in a minute, where we're hiding some of the information. And that obviously makes it difficult to inspect for values or objects or whatever of this sort of thing, because some of the structure is private, some of the structure is hidden, and is only used in the implementation and can't be inspected. And we can encode to some extent function types as existential modules, but I won't talk about that now. So that's the distinction. Why am I interested? Because I think of types as being a kind of space. Types are a syntactic thing that we can program with. We can run programs and see what happens. But I think we can also think of them as spaces in the sense of mathematics. So in the concrete side, we have the space of integers. We all know the real line, maybe the real plane we could talk about. The 2-point space with Booleans in it. And coincidentally, or maybe it's not a chance at all, the concrete types all have fairly familiar sort of high school spaces attached to them, whereas the abstract types have much more interesting stuff going on. I mean, for example, an infinite list could be thought of as saying, describing a path through this infinite tree. This is the Cantor tree, so each step we either go left or right, so that's true or false. And if we've got an infinite list, it tells us a path all the way through that infinite tree. And if we're talking about probability, we're interested in distributions on these spaces. So at the abstract types level, random functions, distributions on the space of functions might include Gaussian processes, which I'll say a bit more about later, and other kinds of random function. On the lists, on the infinite list, it's interesting because to give a probability measure on the space of infinite lists of Booleans is by Kolmogorov's extension theorem to give a consistent set of probability measures on the finite parts of it. So that sort of connects the abstract to the concrete in that particular case. Okay. But yeah, maybe that gets across that measures on these spaces that correspond to abstract types are really interesting from the point of view of stochastic processes or non-parametric statistics, which I'll try and say a bit more about as we go on. So I guess that's my motivation, but I also thought, there are other reasons for using abstract types. So let's talk about those for a bit. Oh, yeah, before we do that, let me just summarize. I'm going to talk about function types and modules specifically in probabilistic programming. And as I said, other people would look at probabilistic programming not perhaps as a language for describing spaces and mathematical constructions, but rather as a practical thing. So I'm going to use examples in this talk which I've built using a library that I've been working on, which really allows me to write the types I've been talking about and allows me to write the programs that I want to write. I've been doing that with Hugo and Swaraj. And I'm calling it lazy probabilistic programming language, but it builds on lots of ideas that have come up over the last 20 years or more. I encourage you to have a look and send me any ideas you have about what we're doing there. So what's another reason for looking at abstract? What are other reasons and so on? In traditional programming, even if you learn computer science a little bit at high school, people talk about high level and low level. I think these have advantages or perspectives from both the engineering and the foundational points of view, right? So for example, high level programming is really good for building up large software systems, putting together modules where we maybe hide some bits, understand which bits correspond to which component. And on the foundational side, those kinds of constructs like functions, higher order functions, correspond across the Curry-Howard correspondence, if you know that, to proofs, and types correspond to propositions. So even without probability there are all sorts of interesting things, I think, in each of these four domains, which let me switch now, though, to when there's probability, because that's what we're talking about here. And then, as I said, in the foundational point of view, when we have abstract types and more interesting spaces, we're led to stochastic processes and non-parametric statistics. On the practical side, of course, that is interesting, but also I think perhaps probabilistic programming in practice could do with more ideas about how to organize and modularize the programming that we do when we're statistical modeling. On the low level, I'm not trying to say anything bad about the low level, and of course, Monte Carlo simulations often or typically work with concrete types. You want to get a real number or a Boolean at the end. And so I'd say they live down here as some practical thing you do at the low level, or any other kind of inference, typically. On the foundational side at the low level, it's fascinating because that leads us to philosophical questions about what is probability. I don't know, Dutch book arguments or whatever you like to formulate things in terms of. So there's all kinds of things I think there that fit into all four of these parts. Okay, so that's what I wanted to say at the sort of motivation. Nice that Cameron mentioned PPS and LAFI going on, because I was thinking as I was preparing what to say that I have very fond memories of, in particular, talking at PPS 2017, 5 years ago, work actually with Cameron. That was nice because we were in Paris and we could talk to each other and eat nice food and everything else. But a lot of the ideas that I talked about there, or we put forward there, sort of led to what I'm going to talk about now in the rest of this talk. So I'm going to start by talking about function types, and then in a bit we'll start talking about modules and So I'll talk about function types, and I'll take it a little bit slowly, just as by way of introduction to probabilistic programming as well. Here's a function. I'm calling it rand_linear. It's written in lazy people, so you can try it if you like, but it's a very simple program that you could write in most probabilistic program, or maybe all probabilistic programming languages. The idea is it's describing a random linear function. So a linear function is parameterized. I should have perhaps drawn a line. You see me drawing a line with my hand. A line is parameterized by its slope and its intercept. So a random linear function, we need to know what's the slope and what's the intercept. And assuming everything's around this sort of range, a sort of uninformative thing to say is to say I draw the slope A and the intercept B from the normal distribution with mean 0 and standard deviation 3. Okay, so I draw A and B, and then I return A and B, the slope and the intercept. I'm going to use that then in a minute for a regression problem, which is the typical way that you would use a random function. So I've got these data points. Typically in regression, you would have 100 100 or 1,000,000 data points, but here I've just got 7. And I'm going to say which function generated these points. And it's not, it's probabilistic regression, Bayesian regression. So we want to know what's the distribution on functions that generated these points. So our distribution here is describing a prior distribution on the kinds of functions that might generate these points here. Let me show you what this program looks like when we run it, because I haven't done the regression yet. I just want, this is the prior, these are the points. Now it's giving us a slope and an intercept. And you can see it looks like a 2D Gaussian. But I want to think of these as functions, not as a point in the AB plane. So to do that, let me rewrite the program slightly. And instead of returning A and B, I'm going to return F, where Fx is AX plus B. So I've converted A and B into a linear function, AX plus B, and then I return F. And you can see the types coming up here, because rather than returning a pair of real numbers, a random pair of real numbers, the slope and the intercept, I return an actual function from reals to reals. And now I've plotted those. I don't know how well that comes across on this platform. So here's just 100 of them. Okay, they're just lines going all over the place. And the idea is that's the prior, and then we're going to constrain it by including those observations in order to get a posterior distribution on what kinds of lines generated the points that we were looking at. So in Lazy People, we have some features for inference. We have a Metropolis Hastings simulation, and I don't want to talk too much about that just now, because I'd rather focus on the ideas of abstraction in this talk, but I'm happy to talk about it later. But briefly, we can define a regress function, and I'll just read that through quickly. So these points are not collinear. So obviously they're noisy observations about a linear function, right? Because no line will fit through all of them. So no straight line will fit through all of them. So it must be noisy observations. So the noise or the noise in the observation is sigma. I'm passing that in as an argument to regress. I'm going to pick that to be 0.1 just now. And then I've got a prior on my functions, and that's the rand linear thing that we defined a second ago, this one. And I've got a data set. The data set is these points. I haven't shown you the code, but it's just seven tuple of pairs. Okay. And it's going to spit out a distribution on functions from reals to reals. And what does the function do? Well, it samples from that prior, which is random linear, and then it loops. This 4 is Haskell's loop over all the data points, and for each one incorporates the likelihood of that data point. So fx equals y plus or minus sigma, roughly speaking, and then returns f. So that's my regression function written in Lazy People, and then I run that with Metropolis Hastings, and I get these. Rather than seeing the lines going all over the place, now we can see the lines that may have generated these data points. Okay. Yeah. So that's random linear functions. And let me talk through this program even more slowly to really emphasize what structure is here. So there's a type constructor called prob. So we've got the functions from reals to reals, but this program doesn't produce a function from reals to reals. It produces a random function from reals to reals. So we've got this type constructor prob, which if you know what monads are, is a monad. Doesn't matter if you don't. So reals contains the numbers 0, 1, pi, everything else. Prob real num contains probability distributions on the real numbers, like the normal distribution that we've been using, this orange one, and the other normal distributions, but other distributions as well on the real line. We've also got, of course, types like prob bool, which contains Bernoulli probability distributions, like a coin toss. Then, as well as that, we've got parameterized distributions, which are functions that return probability distributions, but maybe take some arguments. So normal takes a mean and a standard deviation and produces the normal distribution. And that's it's a function like this. And I'm showing you that because I'm going to contrast it with something else in a second. Right? Bernoulli is something that's also parameterized by, it's a coin toss, but you can specify the bias of the coin. So functions from real num to prob reals contain the parameterized distributions. If I move the prob outside, it describes a totally different thing. If I move the prob outside, it's describing not parameterized distributions, but random functions. So if you like, random parameterized reals. So this contains functions like rand linear. So hopefully you can see why rand linear, which just gives me a random linear function, is very different from normal, right, which is a parameterized distribution. And I find this quite informative that the types in this lazy people library tell us about all these different constructions that we have, just as you might do in, we're talking about spaces, but really inside the language itself. Yeah, so f here that's getting returned is a function from reals to reals, but the whole thing, because we're putting it inside a do block and drawing some random numbers before we return f, is a random function. There's also other things which are important, like I said, probability distributions on the Booleans are the Bernoulli distributions, but we can also have probability distributions on those. And so those are random distributions which you would use in clustering, as we'll see a bit later. Of course, you can keep going with all kinds of type constructs. Right. Yes. So inside this space of random functions, there's some other stuff, and I'm just going to talk about that for a few minutes. Because it's all sitting in Haskell, one of the first things that people often do in Haskell is to learn how to write an interpreter for another language. So this is nothing to do with probability for a couple of seconds, but what you would do is you would define a type of expressions. And these are expressions, they're just arithmetic expressions, really, with real numbers as constants, add, multiply. I've put one variable in there, let's call it x. I haven't allowed all sorts of variables, kept it very, very simple for now. And I put an if then in there, in this little language. And then in a functional language, writing as probably you all know, writing an evaluator is very easy because you walk by pattern matching. You walk over an abstract syntax tree. I could have, we could define a parser as well and so on, but this is what we need for now. And normally you would say that the evaluator takes an expression and a value for the variable and gives back a result. But if I just draw the brackets in, because they're implicit anyway, then it's saying that the evaluator takes an expression and returns a function. So I can now use that to build things inside the function space. In particular, I can first build a random expression. I haven't shown you the code for this, but it's just a sort of a probabilistic context-free grammar. So all I've done is randomly pick things from this data type to build a random tree. And then I can build a random program, a random function, by first drawing a random expression, and then returning eval-e, which is the thing which takes the expression and returns a function. So that's now going to return a random function that comes from a random expression. Okay, I think it's quite a nice example that's used in quite a few places. So let's try using that. We can use it with the same regress function that we talked about before. Yeah, so here I've run it. I've run Metropolis Hastings. I just plotted 3 results, and you can see it's found some different programs that might have generated these data points. Sometimes it's put 2 if then else's in there, sometimes 1, sometimes none, and so on. So that's something else that lives inside the function space. That's another thing that lives inside prob, real num to real num. One other thing I want to illustrate is Gaussian processes. For now, in lazy people, we just implemented the Wiener process, and that's sort of random walk, but it's nowhere continuous. So if you zoom in on it, it just keeps wiggling about even more. Now that goes all over the place, but if we do regression with it, we see this typical sort of Gaussian process regression sort of fitting the Wiener process to these data points. So that also lives inside the space of functions from reals to reals. Okay, that's what I wanted to say about function spaces. Let me now talk about models of this. So we've got all of these types. Well, at least we've got these function types is what we've been talking about. And we've seen examples of probability distributions on them written in code. Now, what do they look like semantically? So to explain that, I'm going to talk about the model of quasi-Borel spaces, which a few of us came up with a few years ago. There are some other models of programming with function space, probabilistic programming with function spaces. Not all of them necessarily fit exactly into this kind of language paradigm that I've been talking about. But the last one's just come out recently, and that does seem to fit to a large extent. So that's quite interesting. Okay, so yeah, quasi-Borel spaces. So quasi-Borel spaces are going to be a notion of space which allows all of these constructors on the spaces rather than on the types. Okay, so we're going to have a type of real numbers, but we're also going to have a type of probability measures on the real numbers. We're going to have a type of functions, space of functions, and we're also going to have a space of probability measures on the space of functions. Okay, to motivate quasi-Borel spaces, the key idea is this, sometimes called a randomization lemma or reparameterization. It's what you use if you're using pseudo-random numbers, really. And that's that one uniform distribution is enough to generate all your probability. To generate all your probability, all you need is this tiny source of source of randomness, which is a number uniformly distributed between 0 and 1, a real number between 0 and 1, uniformly distributed. Okay, so that's the key idea. Once you've got that, that's enough to generate all of your randomness. And that's the idea. Well, that's one way that I would motivate the definition of quasi-Borel space, which I'll show you now. Okay, it's not totally true, and maybe I'll talk about that in a few minutes. So it's not totally true with really general notions of probability. Okay. But what does it mean to generate all probability measures? It means that for any probability measure, let's say on a space B, there exists a function from the reals to B, such that when I push forward the uniform distribution along the function alpha, I get back my probability measure P. So whenever I've got a probability measure P, I can find this alpha such that I can use to push forward the uniform distribution and get back P. In probabilistic programming language, you would say P is always equal to the thing that draws an R from a uniform distribution and then returns not R, but alpha R. Okay. This is also true in a parameterized setting. If P has some parameters A, then we can also find a parameterized alpha as well. That's important, but I don't think I'm going to need it in the next few minutes. Right, so let's look at, just remind ourselves what that's doing. Okay, so in particular, let's look at the normal distribution, because that's not a uniform distribution. But typically what you do to transform a uniform distribution into a normal distribution is use this inverse CDF, the probit function, which converts a uniform distribution into a normal distribution. And if you haven't seen this before, if you look at sort of what roughly informally what happens to the mass of some bit of this uniform distribution, as you push it across the function, you end up with much more mass around the 0 area than you do in the tails. And so it's a function that's going to have a range going all the way off to minus, cut it off here, but it goes all the way down to minus infinity and all the way up to plus infinity. But its domain is only between 0 and 1. Okay, I've rotated, in case it's unclear, I've rotated this bell curve just to show what's happening. So that's one way of generating a normal distribution from a uniform distribution. And we can do that in general for any distribution on a sensible kind of space. Okay, so in quasi-Borel spaces, what we're going to do is take that as a definition. So a quasi-Borel space is a set, an abstract, just an arbitrary set, together with a collection of random elements. And those are the alphas that are allowed. So the idea is you've got something from a uniform distribution. We want to push it forward along an alpha to get a probability measure on the set X. But what kinds of alpha are we allowed to use? And so a quasi-Borel space is a set that's equipped with a given collection M of those allowed functions from R to X that we're allowed to push forward, like the inverse CDF or whatever. Okay, and they should satisfy some conditions that I'm not going to show you, but are very sensible. And the idea is that we're going to interpret the types of our language as quasi-Borel spaces, so sets together with a collection of those alphas that we're allowed to use. And programs, functional programs, will be understood as morphisms of quasi-Borel spaces. A morphism of quasi-Borel spaces is just what you think, hopefully if you think about it, you think it ought to be. So if I've got one of these alphas that takes a seed and gives me back an X, and then I apply an F to it, it won't in general give me back an admissible alpha in Y. But that's the requirement. So F is only good, is only allowed as a morphism if whenever we compose it with an admissible random element alpha in X, it will give us an admissible random element F alpha in Y. Okay. So those are the maps, those are the programs should correspond to those things. Yeah, and so that's how we're going to interpret programs. I ought to show you how we understand probability in quasi-Borel spaces. But that's also quite straightforward, I think. So a probability measure on a quasi-Borel space, remember this is just an abstract set together with a collection of admissible random elements in X. It's just one of those admitted random elements. Because remember, a probability measure is supposed to be something that we can get by pushing forward the unit interval onto X. And so to give a probability measure, we just give such an alpha that's allowed inside this collection M. Now, sometimes different alphas and betas will give the same probability measure morally. So we need to work up to an equivalence relation. So here's one alpha that we talked about a second ago. There's another one that will give the same, although it's a different function on the nose, it will give the same distribution. So it's alpha and beta are different functions, but they'll give the same distribution on the reals, okay, for example. So we want to make those the same distribution. So we do that using an equivalence relation, which I'll define right now. Now, to define the equivalence relation, I need to tell you first what the real numbers are. And that's something we need to do anyway, because we've got a type of real numbers in our language, and we need to say what's the interpretation of that as a space. So the real numbers are interpreted as, well, we've got to give the set. That's the set of all real numbers, as hopefully we all understand that, together with a collection of functions from reals to reals. Those are the things you're allowed to use to push forward the uniform distribution. And the ones I'm going to take are the Borel functions. And if you don't know what a Borel function is, that's fine, but it's something that you can integrate, basically, without worrying. And as long as you haven't done anything crazy, probably all the functions you've ever used have been Borel functions. And I'm going to use that to define when two measures are equal in general on an arbitrary quasi-Borel space. I'm going to do that by talking about tests. So if I've got a space X and a measure on it, an alpha, then I can inspect it by looking at maps from X into the reals. And this, again, I think ties to this idea of connecting the abstract with the concrete. If I've got an abstract space X, I want to look at some concrete things in the reals, which I can actually look at. And that's partly why I'd like to say the reals are concrete for today. So for any morphism from X to R, and I know what a morphism is, that's one of these things. When I compose alpha with K is this test function, then I can integrate it because it's now a function from reals to reals that I can integrate. And by definition of morphism, if you unpack that, it will be a Borel function from reals to reals. So for any K, I can compose it with any alpha that's in M. And if K is a morphism, K alpha can be integrated because this is what the structure on the reals is defined to be. So everything's just by definition. And so if I integrate alpha with respect to K, I hope to get the same thing as if I integrate beta with respect to K. And if I do, then for all K, then I'll say alpha and beta are the same. So alpha and beta are the same if for all K, when I integrate, I'll take the expected value of alpha K, it's the same as the expected value of beta K. So that's one way to explain the quality on measures. Slightly different way, since this is a Popl workshop, is to connect to continuation passing style. And so we say that K could have been, I use K as continuation, what to do next. So in other words, the probability distributions are a subspace of this continuation monad, but only those that come from an alpha. So whenever I've got all kinds of stuff in here, but I only want to take those functionals that come from an alpha. So when I've got an alpha, I can take a K and find the integral of K alpha, and in that case, I'm going to consider that element of the continuation monad as a probability. Okay, so that's another view on the probability monad. Okay, so that's what we have. We have probability measures with this equivalence relation that we took some time to define. And so we have a space of those. I've also explained what the real numbers are. So now we can interpret the types of lazy people or of probabilistic programming language as spaces, as quasi-Borel spaces. And so that connection that I had at the beginning between types and spaces is starting to take shape. Also, I won't go into the details, but it's nice and easy to check that that we can take the space of morphisms from A to B and equip that with a quasi-Borel structure very easily. And that's what we will take as the interpretation of the arrow type, which is just a syntactic thing. So all of those type constructors correspond to spaces now. And everything works quite well. Okay, so that's what I wanted to say about quasi-Borel spaces as a way of giving a semantic model of functions and higher order functions and the abstraction that comes from functions. And it comes really from this idea of random elements. Okay, so let me change tack now and talk about another kind of abstract type. Remember, we talked about functions, also lazy lists, modules, and so on. And I'm going to talk now about modules for a bit. So this is something that we talked about in PPS 2017, as I said at the beginning of the talk. So it's nice to come back to that. To motivate it, I'll give an example, and then I'll start talking about some of the machinery. So consider a clustering program where we want to group some points into clusters, maybe red ones and blue ones like this, or maybe you want to say, well, those three should be in their own cluster because they're so close together, and the rest of them should be separate. Different things you might be able to see if you squint. And the idea of Bayesian clustering is that there's not necessarily one given clustering that's the right one, rather there's a distribution over possible clusterings that we would talk about. And so there's typically like a hidden variable here, which is the proportion of points in each cluster, and that's something we need to infer. Okay, so for each point, we need to know which cluster is it in, but along the way, we probably need to know what proportion of points are in one cluster or the other. So I'm going to show you a model that deals with that now. This is a parametric cluster, and there's only two clusters, but a bit later, I'll hopefully have a few minutes to talk about the non-parametric case. Okay, I'm going to model the clustering to start with using Pólya's urn. So if you haven't seen it before, it's a beautiful idea that goes back, I guess, I don't know, 100 years or something like that. And the idea is to start with an urn, that's to say a bag, an opaque bag or something like that, where I've got two balls in it and I can't look inside, but I can put my hand in and take a ball out. Okay. So it starts out, as I said, with a red ball and a blue ball. And the urn scheme goes like this. We take a ball out, there's going to be half a chance of getting the red one, right? Well, then rather than putting it back, we put back two of them. So if we take a red one out, we put back two red ones. If we take a blue one out, we put back two blue ones. And that's Pólya's urn. Okay, so I'll just run through it to make sure you all understand what I mean. So after I've taken the red ball out, I'll put two back in. So now there's two red balls. So you can see as I take the red ones out, it becomes, oh, maybe it's more likely that we're going with reds at the moment. So then 2/3 chance I'm going to take a red one this time. And then the urn scheme says put back two more red ones. So now I have three red ones and a blue one. There's a slim chance, but a quarter chance that I'll take out a blue one now. And suppose I do, well, then I'll put back two blue ones. And now I end up with 5 balls, 3 of them red and 2 of them blue. So it got a bit more balanced at that stage. But you can see it's totally random what proportion of balls we end up with. So that's Pólya's urn. How could we use it to cluster these points? Well, what I want to propose is to put it into a module. And this is how it looks in lazy people. So we've got the urn, U, and it's a pointer because it's a stateful thing, right? The urn changes as time goes by. We started with 2 balls, we've got 5 balls at the moment, but that will keep changing. And so it's a pointer to a pair of integers, which are, say, how many red balls, how many blue balls. And then there's a function new, which allocates a new urn, right? I might be doing several clustering problems at once, and I might need several urns, or typically I'll just need one, but it doesn't matter. I've got new to allocate me a new urn. So that returns for me a U. And I've got get, which follows that scheme of take a ball out and put back 2 copies of it. So get is something that takes an urn and then returns whether it's whether the ball I drew was red or blue, but under the hood, the state of the urn, the contents of the urn are going to change. I think I've got the actual source code here. Haskell's not a stateful language, so I had to use unsafe before my O and exclamation marks and stuff. So don't worry about that. What I wanted to emphasize, though, is that I only expose to the programmer the type U, new, and get. I don't. The person who uses my module to do clustering or whatever doesn't need to know about the state. They don't need to know about that it's an IO ref, because I didn't export my U. So in Haskell, when I write this, it means only those things can be used by the person who's using my module. And so because I didn't put my U in there, nobody who's using my module can get a handle on the fact that this is implemented as a reference. So this is like a private field in Java, then, if you like. It's a hidden thing. It's an existential thing. It's a hidden thing. And so the fact that it's implemented in this way and the contents of the urn are totally hidden. whoever's using my module can't look inside the urn at all. Now, it turns out that, yeah, it's a hidden implementation. This module is equivalent to a totally different one. And this is the totally different one. I'll talk you through that, and then I'll talk about why they're equivalent. So this different one implements U, right, which was an urn here, a stateful thing, like a pointer to a pair of integers, as a real number. And so U could now stand for unit interval or uniform, let's say unit interval. And again, I don't export my U, so nobody who's using this module will know it's a real number rather than an urn. Again, I provide new and get. They're doing very different things now in this module to in the earn module. Right. So one way to think of this is that the real number we're going to have here is sort of the limiting proportion of red to blues in the earn that we might be using. Now, that doesn't quite, add up, because if you've got an earn at any point in time, you only see some number of red balls and some number of blue balls. You don't know what the final proportion of things is going to be if you ran it forever, and that's sort of not something you want to think about. But that's maybe gives you an idea of why these two modules have anything to do with each other. So this module here, I've written all the code here. There's no state at all. So what does new do? Rather than allocating a new piece of memory and a new earn, all it does is draws something from a uniform distribution and returns that tagged with my U. So it's tagged with my U. No one can actually see that number if they're using the module, but they can pass it around, pass the U around. Okay. So we've got new there, and then we've got get, which takes one of these U's and is supposed to give us back a Boolean. In the earn case, it took a ball out and put two balls back. In this case, all it does is tosses a coin with the bias U. So Bernoulli is just a fair coin toss that returns a Boolean, and it tosses a coin with bias U. So yeah, so that's I hope you can see it's an implementation of the same interface at least, and it turns out it behaves exactly the same. So I think that's a really important fact in basic fact in yes, probability theory, and leads us towards non-parametrics and maybe stochastic processes. But it appears as an idea about abstraction. It's crucial that we can't look inside the earn, which is dealt with by having this hidden type. And it's crucial that we don't inspect the real number. We don't know what the ultimate ratio of reds to blues is without running the program forever. Yeah, so these two programs then, modules, are the same. And this is something that we talked about in 2017, and then we managed to prove a year or so later. And I really struggled for a while to prove it, because, as I said, we can't sort of do a naive by simulation proof, because we can't match up the state of the earn with a particular real number, because it's changing over time. The way we proved it in 2018 is via Hilbert post-completeness, which, say, what we did was we wrote down the equational theory. So we said, what kinds of programs can we write with new and get? And let's write down some axioms. And we came up with a few axioms, of which there were really only three crucial ones. And then we showed, it's quite easy to show that this module and that module both satisfy those axioms. Marcin Simczak showed that for this case using Lars Berkedal's program logic for probabilistic programs. And so there was basically three, some bookkeeping axioms, but roughly three axioms. And then we showed, which I was quite surprised about, that there could be no further axioms. Very, very strong completeness, sometimes called Hilbert post-completeness, which means any further axiom to the ones that we'd written down would be contradictory. So in other words, the fact that these satisfy those three axioms, they can't satisfy any other axioms, because they would fall apart if that happened. So they must therefore satisfy the same equations, and they must be the same module. Later with Bart Jacobs, in fact last year, I worked, well, I guess 2 years ago now, I worked out a more co-inductive argument for explaining what's going on here. Just as an aside, I'll comment, because we talked about models of function spaces. What about models of abstract types? Well, what we can do, and I think this is in Dario's PhD thesis, which he just passed his Viva a couple of weeks ago. We can use this equational theory now to build a syntactic model of probabilistic programming, right? Where we just literally put in the syntax, quotient by the equations that we've written down, and that's then a model of probabilistic programming. So we can use that to build a new model of probabilistic programming that's not the same, not coming from measure theory or QBS or anything like that, but just a purely combinatorial syntactic thing. I thought that was quite interesting, and sort of pushes the way towards new, more syntactic or synthetic models of probability or of probabilistic programming. Okay, so that's Pólya and uniform distributions. But we could also ask, is it really specific to Pólya's? If we had another stateful module with this same interface, could we also give for that module an equivalent module without state that used probability instead? And the answer is yes. And this is De Finetti's theorem. Okay, but I don't think we've managed to formalize that quite yet. But De Finetti's theorem roughly says that for any stateful module with a certain property, we can find an equivalent module that doesn't use state. And that happens when the model satisfies the Dataflow property. I suppose it is kind of formalized in my paper with Bart Jakob. So let me explain the Dataflow property, because I think that's really important as a sort of abstract concept of probability or of probabilistic programming. Basically says, something that compiler writers do all the time. You need to know when you can reorder the lines of a program. And so Dataflow property says that you can do that. So if I've got this, coming back to the beginning of the talk, this random linear function which generates an a and a b and then returns fx equals ax plus b, I could switch around the lines a and b. Now it might, in terms of the simulation, it might make a very small difference to what actually happens, but roughly these programs will behave in the same way. So we could say, if we draw the graph of these programs, forgetting about the control flow, but just looking at how the data A as U and B are used to build the F, then the topology of this Dataflow diagram doesn't matter. Is all that matters. So if I rearrange these first two normal draws to go the other way round, it's the same diagram, topologically speaking, and so we say it's the same. It's the same program, and that's the Dataflow property, that you can do a sort of topological transformations on your Dataflow diagram. One other thing is that we could also, I've written this program. It would be a bit silly in this example, but maybe it would happen in a bigger program. I could introduce another variable C, which is also normally distributed, let's say, but then never use C. So C was never used in what followed. And so if I draw the Dataflow graph, here's C, and it just gets thrown away, if you like. Garbage collected or whatever is never used. And so these two diagrams are also regarded as the same. We can get rid of that line. It doesn't change. It would change the Monte Carlo simulation, perhaps, depending on the algorithm, but it won't change really the ultimate distribution that you get at the end. Okay, so that's the Dataflow property. And as I said, if you've got a stateful module, so the Pólya it takes some effort to check this, satisfies the Dataflow property. So if I call get and then get, I can reorder the results of those two gets, even though the earn was in a different state in between, and I can't observe the difference. So that's what Martin showed, as I said, using Lars Bergedal and Adik Bijak's program logic, that you can reorder the draws from Pólya's earn. Well, Pólya showed it, but Martin showed it using program logic kind of way. Okay, so another question is, can we, if we change the interface to use a more fancy thing, right? So rather than just a U, what if we've got a U and a V? And what if we, as well as getting a new U, we get a U, and from the U we get a V, maybe get takes a U and a V and returns a Boolean. Can we also say something like that? Can we go from a stateful module to a purely probabilistic one? And that's something I've been working on over the last few years. So now we're getting into sort of the end of the talk and some things I've been working on, I guess. And we had a paper last year with these probabilists, Paul Jung, I suppose, and Jiho Lee, about a sort of piece of probability theory, saying when we can find Aldous Hoover representations come from program or signature modules like that, interfaces like this, describing some sort of more interesting interactions. But I think we haven't fully proven this yet, and I think to fully prove it, we would need stochastic memoization. So I'm going to finish up the talk by talking about stochastic memoization, which I think is another really curious abstract idea in probabilistic programming. Okay, so we've talked about random functions, we've talked about modules, and now I'm going to talk about stochastic memoization, which is sort of connected to both. It's connected to modules via this conjecture, and it's connected to functions, as we'll see in a second. So memoization is a very old idea. It was first called a machine learning method. Memoization means remembering the results of something as you run it. So, if I calculate this, if I ask my children what's the square of 57, then after grumbling for a bit, I guess they'll do 7 times 7, 49. 5 times 7 is 350, and then add all the numbers together, get out 3,249. If I ask them what's the square of 3, they're going to 369. Then ask them again what's the square of 57. They'll be quicker ideally they'd be quicker this time, and they'd come back immediately with 3249 because they already calculated it. I could then ask them what's the square of 42, and so on, keep going like that. So the idea is that we could also implement this inside a programming language, and that was the idea way back in 1968. Now, in the probabilistic setting, it's interesting because it changes the semantics if we memorize the results of random calls. Let me explain what I mean by that. And I think it's important because it's a way then, as you'll see, of building infinite dimensional structures, of building new things inside the function types. So I want to think, in lazy people, there's a function called memoize, and it takes a parameterized distribution, a function from A to prob B, and turns it into a random function from A to B. So all we've done is move that prob from inside to outside the brackets, if you like, but that's doing an awful lot of stuff, basically making all the random choices all at once. So one way to think of it is to say, here's your P, which is a parameterized distribution with a parameter from A and gives you back a distribution on B. So for each X, I'm going to draw something from PX, which is a distribution on B. So that gives me, for each X, it gives me a B, a canonical, chosen B. And then I put all of that assignment from X to the thing in B as a function. And that assignment as a function is what I return. Now, I made random choices along the way. That's why the probability monad is wrapped alongside there. So when A is a finite type, you can implement this very easily. You just loop through all of the inhabitants of A, calling PX for all of them and getting a result, and then joining them all together into a function, a little table, and returning that. Even when it's like the integers in Haskell, you can define it using Haskell's laziness. So that's quite nice, something maybe that uses some of the ideas of lazy people. But when A is uncountable, then it's a bit harder to understand what's going on. What does it mean to randomly pick PX for all X when X ranges over an uncountable space? So another way to see it is this way that we talked about, where that's done when you implement a compiler or whatever. So when I call memoize P, it's going to give me back a function from A to B. And so if I ask what's f of 3, only at that time does the randomness happen. The randomness is delayed until it's actually needed. And that's when I go, oh yeah, okay, I'm going to call P with 3. That's a parameterized distribution. And I do some randomness and I get back 23.6. Then I call F with, let's say, 57. So I need to call P with 57. That gives me a distribution. I draw from that. I get maybe 17.5. But then again, somebody says, what's F of 3? And then rather than making the random choice again, I remember in my lookup table that it was 23.6. And then we can continue, and maybe sometimes we'll make random choices, sometimes we'll look in the lookup table. So I implemented it in lazy people. As you can see, I've used state again. Don't have to read this. But yeah, we have memoize there. And it's fascinating because we could come to the Dataflow property. So when I memoize a random when I memoize a parameterized distribution, I'm using state in my implementation, but I would conjecture it still satisfies the Dataflow property. I can always, if I use memoize, even though it's using state, it's hidden state, and it will always mean that I can reorder the lines of a program just as I can with probability distributions ordinarily. So memoize doesn't break the Dataflow property, I conjecture. Now, to prove it, we would need to find a model, a semantic model of memoize, and that's the open challenge, which I think we've just about solved in some restricted setting with Eunice, and we'll hopefully write that up soon. Okay, so that's memoize, which converts a parameterized distribution into a random function. Let me just finish by that was a technical function, memoize. Let me show you how you might use it, and then use that to sort of wrap up the talk. So memoization, I'm going to show you how to use it in clustering. Let's use a non-parametric clustering. So I talked about clustering before. Let's suppose we don't know how many colors there are or what colors we're going to use. So we might have reds, blues, and yellows. And rather than saying there's some proportion of reds, we don't know what proportion of things there are. So let's say there's an abstract type of colors. Okay, I won't show you the full implementation, but we could do something like this. And then, they could be any colors, we don't know. And suppose these are people and we want to know, are they going to vote Republican or Democrat? We're doing an election model or something like that. We need to assign to each cluster what are they going to vote. So for each color, we need to draw something from a probability distribution. And we can do that using memoize like this. So this is the distribution on the Booleans. This is a parameterized distribution on the Booleans that given a color gives a distribution. It doesn't use the color, but it returns the fair coin. But memoize gives us a random assignment of vote outcomes to colors. So we can use memoize in that way. And then we could perhaps tie it up with a Dirichlet process to generate different colors and get a full model of some sort of election prediction. But the thing I want to say is memoization isn't essential if you just look at the whole program that I've got here. In the end, all we want to know is who's going to vote this way or that way. And so we just want a Boolean at the end. Or maybe, we just want a random Boolean at the end. But it is very useful in describing the model in an abstract and compositional way. And indeed, perhaps abstraction is never essential. We talk about function types and higher order functions. You can always boil it down to just getting back a real number or a Boolean. But from an engineering point of view, it's very useful to have all of this interesting structure. I think conceptually, mathematically, it's very interesting to have all of the interesting structure that comes in the abstract types and the modules and higher order functions. People used to say real programmers don't use Pascal, right? But maybe real statisticians should use abstract types. Okay, so those are the concrete types. We talked about some abstract types. We could talk more and more about that. But let me leave it at that for now. We've talked about random functions, we talked about modules, and then we finished up talking about memoization. Thanks.
Yeah, thank you very much. Yeah, that was a wonderful talk. Thanks for speaking at the beginning of this workshop today. Yeah. So if you haven't yet looked at the Q&A tab, please click on that, and you can both upvote existing questions and also add your own questions. So I'll begin by turning it over to Ohad, who can ask his question about Pólya's urn, and then he'll handle the rest of the Q&A. So thanks again, Sam.
Thanks, Sam, also for a great talk. A question about Pólya's urn. Existential types usually have some meta-theoretic results about parametricity or free theorems. Yeah. Have you merged these ideas into your proofs, or do you think they can add something in those proofs, or what's needed to integrate them with those proofs?
No, that's a very good question. I mean, we were just pleased in 2018 to get the result, to be able to sort of give a formal argument as to why these things are the same. And then, as I said, we have like a co-inductive argument, but you're right, it doesn't connect to more general arguments about parametricity. And I tried to use some of those arguments. I guess they're not typically for probabilistic languages, because here we've got both states. Well, maybe I should have emphasized a bit more. In the one module, we've got states, but only finite probability. In the Pólya's urn, we don't need to talk about real numbers. So there's maybe some reasoning systems for that. But then in the other module, we haven't got state, but we have got real numbers. So you would need, in order to relate the two, you need some sort of system for understanding all of that. But yeah, I think it goes on, because then if you want to have first-class existential types, for example, that would be very, very interesting. And I don't know how to model that. At least for probabilistic systems. Yeah. Does that answer your question?
Yes, thank you. We have a question from McCoy Becker. Can you bring him to the stage, please?
Well, I can read the question. So it says, do you mind reiterating the importance of Dataflow property in the context of programs defining prob A? I could sort of see how it's related to Definetti, but I think I'm missing the punchline. Okay. Yeah, sorry for that. So so the Dataflow property says how we can reorder the lines of a program. Now, if I have let's say Pólya or some stateful process, then the Dataflow property is saying I generate something and then I generate another thing. Then I could have generated those in the other order and returned them, or equivalently, I could have returned them in the opposite order. Maybe that's a better way to say it. So I don't know if I can share my screen again, or if that's not going to. Am I still sharing my screen?
You should be able to.
I think I am. It says I am, but I think the question has come up. Oh, there we go. Yeah. Thanks. So if we look at the example I had here, so the example I have here, right? Okay, we're not drawing from a stateful thing, but suppose instead of normal we had something that was stateful. Right, in both these cases, then we're effectively returning A and B, and in this case we're effectively returning B and A. So what's happened is we've got a distribution where we're returning A and B in this case, and in this case, in the second case, on the right hand side we're returning B and A. So we've switched around the things. Now the usual formulation of the Finetti's theorem would talk about reordering things. So what this is saying is that we return A comma B, it's the same as returning B comma A. And so that's, I guess, talking about the usual formulation of the Finetti's theorem in terms of exchangeability or reordering. Does that, I don't know if McCoy's still here, but does that help?
Yeah, he says it helps, thanks.
Okay. And I suppose, I mean, just to, I sort of feel like the Dataflow property is important because it's talking about, it's sort of encoding that notion of exchangeability and reordering in a programming setting. I should probably say, I think Cameron, Nate, and Dan wrote a paper in PPS 2016 emphasizing that, and that's maybe why I got interested in it. So the Dataflow property talks about reordering, but it's also essential to have this abstractness of the urn, that you can't look inside the hidden state as well. And so those, I guess it's quite cute that, or beautiful, that those two concepts from programming language theory, both data hiding the contents of the urn, and reordering coming from Dataflow property, correspond really to what's needed for the Finetti's theorem in terms of exchangeability.
Thanks. If anyone has any more questions, they can raise their hand. In the meanwhile, I can ask another question of mine. About memoization. So your example doesn't involve conditioning. Is there anything you can say about that, either in the foundations of it or the implementation side in lazy people?
Yeah, on the implementation. So for conditioning, there's no problem in implementation. We certainly did some examples of cluster. I mean, showed you a very simple example with finding a vote share, but we did some simple examples, more elaborate examples using memoization. It's not a problem with conditioning. Was that yeah, I mean, semantically we need to understand. I'd like to understand it without conditioning first. But what was I going to say? Oh yeah, I suppose one point is that I think maybe Cameron or Dan has emphasized before, is that when you have these stateful stochastic processes like Pólya's urn, where the contents is changing over time, conditioning in Metropolis Hastings is slightly more subtle, because you want to often roll back or go back to another situation where you were in, and if the state has changed, it's a little bit hard to know how to manage that. I mean, it's fine, but I think what may happen is that sometimes the state ends up getting very big, or there's a lot of garbage to be collected, and so that's something I think that's definitely worth investigating. In Church, for example, at some point they had something called unsample, which would allow you to undo a sample. We haven't looked into that yet in lazy people, but we didn't run into problems per se.
Thanks. Effects are still interesting in probabilistic programming.
Yes, and the hiding, I think, hiding the effects and understanding the hiding the order of the effects is interesting and important. Yeah.
Okay, thank you. So I'll ask more questions offline, I guess, and let's thank Sam